In this example, we have the same four variables, two integers, x and y, and two pointers pointing to integers, x pointers and y pointers. We make x equals 10, and x pointer points to the memory address of x, and then we dereference x pointer, which gives us the value of x, and that value is 20. What do we get in this print statement? Well, notice that x has already been changed. Instead of doing x equals 20, what we do is we use the indirection or dereference variable extras, x pointer, right, and assign a value of 20 to it. So when we print this out, x actually now bears a value of 20, not 10. When we dereference x pointer, we get the value of the object, which is x, that x pointer points to. So this is 20 because the value of x is 20. What does this tell you? This means that instead of assigning a value directly to x, we can use indirection operator or dereference operator on an integer pointer that points to x to change the value of x. This is a very powerful concept in C and C++. Let's look at yet another example next. Here we have chars instead of integers. We have first and second chars, and then the third variable char pointer, which points to the address of first. First has a value of A, second has a value of B. So when we dereference P, we're getting back the value A right here. So this is the reason why we see A. This is character A, which has an integer value of 65 in the ASCII chart. Let's look at the very next one. P equals ampersand second. The reason why we can do that is because P is a pointer. Pointer is assignable. So we assign P now to point to the address of this unary operator, address of second. When we dereference P, now we get back the value of second, which is B. Again, this is a character B. Let's try this again. Now P is back to the address of first. Notice that we had it as address of first, then the address of second, now back to address of first. We dereference P, and by way of dereferencing your pointer, which means that you're applying an indirection operator on this pointer, you get back the value of the first, and you're assigning this R value to be the value of first. So at this point, you have just set first to a value of Z. Let's look at this again. P now equals ampersand second, which means P now has the address of second. When you dereference P, you're changing the value of second. So second now is going to have a value of Y instead of B. This is the reason when you print first and second out, as we illustrated before, second now has a value of Y. First remains Z because we just did it right here. Now let's look at these two lines. What is the result of P when you print it? Well, remember when you C out or using printf in C, you're getting the value of P. So what is the value of P? P is a pointer. So this is something to the effect of 0 times something. This is hexadecimal. Someone else's memory address. What is that memory address? The memory address of the second right here. So this will print out the memory address of second. When you dereference P, you'll be getting back whatever that second value is, which was Y right there. Hopefully this illustrates enough of examples in relations to how ampersand, extras, these two pointer operators are in use. Let's look at the next slide. This slide illustrates something is wrong. What is wrong with the following? Let's take a look. Again, we have the same four variables, two integers and two integer pointers. X equals 10, but look at this. When we dereference X, we assign a value of 20 to it. But how would you dereference X pointer? What is X pointer? X pointer is a null pointer. So basically what you're doing here is you are dereferencing a null pointer. Remember, a null pointer points to a memory that does not exist. This memory that does not exist could be 0 times 00000 or 0 times FKW 5, etc. doesn't matter. This could also be other implementation defined value, as long as it can never be a real address. If you run this code, or simply this one in C or C++, you'll be getting an undefined behavior. In fact, both C and C++ standard says that dereferencing a null pointer is an undefined behavior. Absolutely anything could happen, right? The program could crash. It could continue working silently. In some of your compilers, you may not even get a warning or errors. It could erase your hard drive maybe, although that is rather unlikely. In some other instances, you may get what's called a segmentation fault or access violation if you try to do so, which will almost always result in your program being terminated by the operating system. So you gotta be careful whenever a dereference operator is applied. You gotta make sure that the pointer actually points to something, some L value that refers to an object in memory space and not an R value, which is a constant. If you have done some work in C#, this behavior is akin to null reference exception, or in Java, a null pointer exception. This just means that in C# and Java, the language standards are more helpful than in C++ because they throw at least some null exceptions for you to catch. But this is not the case in C and C++. One last thing, since we study both pointer operators, note that ampersand, address of, and the start indirection operators are complementary of each other. This means that if you have, let's say, both x and y as a pointer to an integer, and you do start ampersand x, you should get back an x. Both are equivalent. Or if you do this ampersand start y, you should get back a y. Just remember, both ampersand and start are complement or an inverse of each other. And these two relationships hold true in C and C++. This should complete our discussions on pointer operators.